Everyone, welcome back again. Now, what did we do until now? Let's see that. So here we go, exploring loops and iteration. That's our topic this time. And what we have done so far are the following. We understand that brute force repetition isn't good at all. Exploring looping with while, decreasing or increasing way. So decrementing, incrementing, which one ever. And then our for loop to stay same way again. Do while we have done as well. Now the next one what we do is understanding when you would use each of these using statements. Okay, so here we go. This is it. Understanding loop equivalency. After having typed in both versions of each loop and run them, you may have begun to see some similarities between each of the looping statements. In fact, for counter-controlled looping, each of them is readily interchangeable. So to illustrate, let's examine each counter-controlled loop by comparing each of their essential parts. The counter-controlled while loop has the following syntax. You see counter initialization, while continuation expression, and then statement body counter increment. Notice that both counter initialization and counter increment, so both of them, have been added to the basic syntax of while. Loop, and then they are somewhat scattered about. So again, so notice that both counter initialization and counter increments have been added to the basic syntax of the while loop, and that they are somewhat scattered about. The counter-controlled for loop has the following syntax. So counter initialization you see here, continuation expression you see here in while, and counter increment you see here inside the statement body, right after the statement body, the increment. In the for loop it's inside the original loop statement. So it would be perfectly logical to assume that the for loop is really just a special case of the while loop, right? The counter-controlled do while loop has then the following syntax: counter initialization, do statement body counter increment, and while continuation expression. Notice that as with the while loop, the counter-controlled expressions have been added to the basic syntax of the do while loop, and are also somewhat scattered about the loop. For counter-controlled loop, the for loop is a natural first choice over the other two. Nonetheless, any of these may be used. However, when we look at sentinel-controlled loops, these equivalences begin to break down. We will see that the while loop provides far more general use in many cases, especially when looking for a sentinel value to end continuation. Now, understanding unconditional branching, the do's and mostly don'ts of goto. The goto statement is an intermittent unconditional transfer of program execution to this specified label within a function block. Goto causes execution to jump to the label. In current C, unlike the bad old days, goto may not jump out of a function block, and so it may neither jump out of one function into the middle of another, nor out of one program into another program. The goto statement consists of two parts. First of all, there must be a label declared either as a standalone statement as follows: label underbar identifier, or as a prefix to any other statement like label underbar identifier, and you see these column, right? Added to the statement. And secondly, there must be the goto statement to that label identifier, so label underbar identifier. The syntax for the goto statement is as follows: so goto label underbar identifier semicolon. The reason for the goto statement being shunned comes from the bad old days before structured programming. The main tenet of the structured programming was one entry point, one exit point. We don't hear much about this anymore because programmers have been trained better, and languages, also starting with C, have been more disciplined, so that goto is not really needed anymore. The aim of the structured programming movement was to counter the spaghetti code of earlier programs where goto ruled because a more disciplined mechanism didn't exist. And the use of goto in some cases had got completely out of control. Programs jumped from here to there and to anywhere, and code became extremely difficult to understand or to modify because the goto statement made it impossible to know all the possible flows of the control. Often the answer to a question, how did we end up here, or what was the code path that got us to this point, was not easily discernible. But thanks God, and thanks to C and subsequent derivative languages of C, the undisciplined use of goto was reined in. The creators of C felt that there was occasionally, albeit rarely, a need for goto, and so they left it in the language. In C, goto is highly constrained in terms of where it can go to. Unlike the bad old days, you cannot use goto in a label inside another function. You cannot use goto out of the current function. You cannot use goto in another program, nor you can use goto somewhere in the runtime library or into system code. All these things were done, and were often done for expediency, only without regard to the long-term maintainability of the code. But no longer, at least with respect to goto. Today, in C, the goto statement can only jump to a label within the same function. GoTo is extremely handy then in the case of deeply nested if statements or deeply nested looping statements when you just need to get out and move on. While this is sometimes necessary, it should be considered rarely necessary. It is also handy at times in high performance computing. So for those reasons alone, we consider it here and we talk about GoTo here. Besides, C provides two other extremely useful and disciplined statements that rein in indisciplined and chaotic use of GoTo, as we will see in the next section. For the remainder of this section, we will look at structured uses of GoTo and how to implement the looping statements we've already seen using GoTo. In each case, there is a pair of labels identifying the beginning and end of what in other statements would be the loop block. In our first example, the end of loop label is not needed. It is there for clarity, as shown in the following example of the sum capitalized N via GoToDo function of the Gauss GoTo program. Okay, so let's see this and let's start our function, and not just the function but the program itself. So as usual, include stdio and then include stdbool, because we need the boolean here as well. Then the function prototype int sum n via go to while. Is this the correct one or is this the other one? Let's go to do first. Okay, go to do first. Go to do. And then int n. And this is actually the equivalent for go to, so int sum n via do while. Again, int n, and we are good. Okay, so we create the go to do first. But also let's add immediately int main this part so that we don't forget it, and return 0. So int sum n via go to do int n sorry, let's do it in this way better. Int sum is 0, so initialization of sum and initialization of the I used to say counter, but now I should say the counter increment, right? So the counter initialization, num equals 0, and then begin loop with sum plus equal num plus 1, num plus plus, keep it the same way like in a book it is. So if num is less than n, go to begin loop. So go up and repeat the loop. And else way is else fall through out of the loop. And loop, we come again here, and loop return sum. Good. Let me check if this is completely correct as well. Supposed to be alright. What we have to do is the following. So int n and then print f the sum of 1 to d is equal %d and via the do like go to loop. Next line we come out, and then n variable we use, and here the function, so sum n via go to on the bar do n and actually I hope that we finished well. Okay, let's try to run this, but Gauss go to, so we will update it over and over. Let's just do Gauss. So Gauss go to see, we got it. No errors, no warnings, and we are good. So this is it. So in the sum n via go to do function, we find all the elements of the preceding looping statements. there is the loop block beginning the loop. Here you see, and then the label. I mean, that is the beginning loop label. There is a loop block ending the at the end loop label. And in this example, the body of the loop block is executed exactly once before the loop condition is evaluated. This then is the go-to equivalent of the do while. So you might now wondering what the go-to equivalent for while loop might look like, and let's do that this time. So here the go-to equivalent while loop, and we just create it quickly. Int sum n via go to while int capitalized N, and we continue with the curved parenthesis, and int sum and int I did a semicolon, so int num, which is standing for the counter, begin loop if, and this you already remember, num is less than num n, go to and loop and then sum plus equal num plus 1, and the increment, so plus plus, go to begin loop and end loop label with the return sum. Okay, we need to get this one too correctly, so here we have this go to while print f the sum of 1 and percentage %d for the integer, again percentage %d for the integer, and this is a where we have to add n and sum n via go to while, and this is going to be n again, and here semicolon. Don't forget, please, not like I just did and I did it wrongly. So this is good, then this is also good, and what is it exactly? How does it call in here? So via while like go to loop. Good. And here we need to do the following as well. So int sum n via go to while int n. And we are good to go. Supposed to be fine to work with, and yeah, it doesn't work, so something I did wrong. that's what I have to also check out this time. So int sum n via do while, here we have it, and int sum 0 int do while we had, and sum n via while, and this is it. Okay, while. Oh wait, I don't have here. Come on. And via go to while. Here we go. Begin loop. We got it. So if this is what we have forgot here. None is less than n. Okay. Go to and loop sum plus equal number plus 1. Okay. Go to begin loop. This time it should work. And yep, that was the mistake here. The parenthesis was forgotten, and that's it. We can get back to our presentation file again. So you see here, this must be corrected, or must have been corrected. So notice how the loop condition had to slightly be modified. Also notice when that loop condition is true, we go to the label that is after the go to begin loop statement. This is the only way we get out of the loop, just as in the while statement. Finally, we can implement a for loop with go to as well, as shown here in a sum n via go to for function. We do that too. So let's start. Int sum n via go to for int n. This is so far correct. Then int sum equal to 0, int num is equal to 0, and then we initialize, so int I is 0. This is to be set initialize counter. Then we start with begin loop label, and again if, and don't forget what I forgot the last time, so here I is less than n, go to and loop and we got here sum plus equal, and again num plus 1 as always we did, and then num plus plus, or actually here it's not num, it's I plus plus, and num plus plus, sorry, both. So that's the correct way. And go to begin loop until it's true, right? And we got here, this is the counter increment, And we can finish now with the next label. So end loop return sum. Now I have to take this one again and copy it, an int n, and here in the print f we need to take this again, this the sum of 1 to %d is again %d, and this is the via for like go to loop, and the new line, don't forget please, then comma n and comma our function including n as parameter. Okay, let's try to run it, and we have already here one more issue because I mistyped it, but and now we have a problem. So we got a sum of 1 and d, and you remember, well, you might remember we have made some kind of mistake then, for sure. There you go. Okay. Certainly that would be wrong, but certainly this would be correct. So again, case sensitivity we forgot, or I forgot, but you see I corrected immediately when I see what the problem is. And that's what you also have to get used to. So why do I type it in? Not because of my it's a fun, but why? Because whenever I type in, I learn with that. So that's why you should do it by yourself, please, as well. Now let's see. Now to have this function correctly, you see it here as well. We had to add a local counter variable. We had this I. Initialize it to 0, test that its value was not less than n. Okay. And finally, increment it before we unconditionally branch to the top of our loop. So you should be able to see how each of these statements correspond to those in the for statement. In assembler language, a nearly direct translation to machine language, there is no for, while, or do while loops. There is only goto. This goto looping constructs could very well be translated directly into either assembler language or directly to machine language. But we are in programming of C, so the point of demonstrating these constructs is to show the equivalence between the various looping mechanism. The main function of the Gauss goto. Well, I think we have done this, right? Yeah, we have done this, because otherwise I couldn't have run it. You see that? And if you created this the same way, then you have finished with the tasks now. And the preceding program, actually, you could see that each of the alternate 3 looping methods to calculate the sum of 1 to 100 gives the same result as we have seen before. So now the question before us is, we can loop with goto, but should we? The answer is quite fine, don't. We don't need it at all. We use for, while, or do while instead. These complex looping statements exist to make our code clearer as well as to obviate the need for goto. Let the compiler generate the goto statement for you and for me. So for general purpose computing, goto should be rarely used, if ever. Remember, the overuse and the improper use of goto is a way of error. Use goto wisely. Okay, now controlling loops with break and continue is our next point where we have to continue. Rather than relying on goto to get out of sticky situations inside of deeply nested statements, the creators of C provided two very controlled goto-like mechanisms. These are break and continue. Break jumps out of and to the end of the enclosing statement block, whereas continue is used for looping, which goes immediately to the next iteration of the looping statement, skipping any statements that would otherwise be executed in the loop after the continue mechanism. We have previously encountered the use of break in a switch statement, where break caused the execution to resume immediately after the switch statement block, and break can also be used to jump to the end of the enclosing statement body loop. In the following is prime function. Break is used to get out of a loop that determines if the given number is divisible by the counter value. If so, the number is not prime. The isPrime function of the primes C, so let's see also the prime C program can be seen in the following code block. So let's do that. And I start again with the main function here rather than anything else. So include stdio h, include stdbool h, so the libraries we need. Okay, we don't need, we need bool. So function prototyping is prime int num, and we do more later. Is this the bool? Is prime, right? Good. So int main is again a void here and return 0 first. And bool is prime int num, and we need this full statement. So here we go. If num is less than 2. Okay, good. Return false if num is 2, return true. We could also do the following way so that it's perfectly aligned. Then bool is prime true. So make initial assumption that the number is prime. Let's also add this comment here, make an initial assumption that num is prime for int I equal to I is less than num, and then increment, so I plus plus, and then if num, if num modulus I is equal 0, then do the following. So is prime obviously false, and break, and here return is prime, and we are done, but not yet completely, because right now we can't run it. So I also need to do a little bit more, but for that I guess we have to go a little bit deeper. Okay, here we are demonstrating break is in a rather simple example. In this case, you may recall we could also have simply used the return false instead, but where is then the fun? Books asks. So because break isn't in a switch but in a loop, break takes the execution out of the loop to the very next statement after the closing loop bracket, so the curved bracket. And then the continuous statement only works within an enclosing statement body. When encountered, the execution jumps to immediately before the closing curved bracket, thereby commencing on the next continuation expression loop and possible loop iteration, only if the continuation evaluates to true. So let's see. We want to calculate the sum for all prime numbers between 1 and n, as well as non-prime numbers in the same range. We can use the isPrime function within a loop. If the candidate number is not prime, do no more processing of this iteration and begin the next one. Our function that adds only prime numbers would look like this, so some prime. You see here, function of the primes c. So let's do that prime c this time. We start with the function prototyping, int some primes, int num, and obviously some non-primes we do as well. If you already do some primes, then why wouldn't we do some non-primes? And then let's continue with some primes first. Int some primes, int num, then the curved brackets we need int sum, and then here we go for int I is equal 1, then the condition num plus 1, and then semicolon again, and the counter we need. And then now curve bracket. So if is prime I, then continue. Printf percentage %d, so integer and I, and then sum plus equal I, and we close this here, and this time let's also wait a second. So this we haven't got any use, so good. Where am I now? Sum. And it's printf. Just to the next line. Don't forget the semicolon again, and return sum. Semicolon again. Well, hopefully it works this time. I would like to save this as primes C. Okay, we have nothing yet here, but the point is we have no error, no warning. That is actually that it works. Good. So let's see what the description says about this part. Similarly, a function that adds only non-prime numbers would like we would like to do. So let's do that. And I already did here. So only one thing I need to do. Just copy this. We know now that it works fine. And we can continue from here. So int is some non-primes. Int sum, this is good. So int I equal 1. Again, I is less than num plus 1. And the counter incrementing, and then here we go is prime, so non-primes is prime, then continue and print di, and this is okay, this is okay. We are done. Let's try to run it. No errors, everything fine so far. Good. Now let's move on. Now here, care must be exercised when using the continue statement to ensure that the loop counter update is performed and not bypassed with the continue statement. Such oversight would result in an infinite loop. Hopefully it's not an infinite loop which we have right now. The main function of prime C, which illustrates break and continue, does three things. So first, it does a simple validation of our isPrime function using a for loop. Then it calls some primes via the printf function, and finally it calls some non-primes again via another printf function. If the program logic is correct, the sum of both prime and non-prime numbers should be the same as our preceding summing functions. That is how we will verify the correctness of the program. The main function of the primes is the following, so we have to create that and have to modify that. So we have first the library is included, then the function prototypes, then here we go with int main void. Okay, so int main void. For int I is 1, semicolon, please don't forget, I is less than 8, and I plus plus, then printf, printf %d and an arrow like this, so equal or larger, percentage s prime, and so it's an arrow and then n, and what we need is I and then is prime. I, remember what we have here. So this is the, again, if yes, and if not, then not. And we are good with this here. Then we can go with the next printf. This time it's a new line. And then we go with printf again. We have to get back from our for loop. Printf sum of prime numbers 1 to 100 is equal to, actually the book says like this, so is equal to d, %d, and sum primes 100 and we need this again, this printf sum of non-prime, this time non-prime numbers from 1 to 100, and you see correctly, and sum non-primes 100 again, return 0. Fine. Okay, now let's hope that we made no errors. Oh God. I don't want to show it right now. So let's see what we get here first. Okay, here you go. Not prime, 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 not prime, prime, not prime, prime. Good. Let's see. And I think we need to do a little bit more than this. So this is the problem here. Okay. Let's add this one too. And let's see how it looks like this time. Well, it looks so-so, but it doesn't look the same I wanted it. We got everything correctly. Okay, let's see if this is correct now according to the book as well. Okay, we got this here from the book. 1 not prime, 2 prime, then 3 prime, 4 not prime, 5 prime, 6 not prime, 7 prime. Good so far. Then 2, and etc. etc. But why don't I got it in a way? We need to examine that point here below as well. Yeah, because these numbers are not correct. I mean, correct but not correct in a way that they are not separated. Now they are separated. Now they look good. And now we can check again with our results if they are correct or wrong. And I think that this time everything is correct. Here we go. 2, 3, 5, 7, good. 1, 4, 6, okay, good. And you see, actually, if we compare it to the book as well, 1060 and 3990, which are again correct. And the 1060, if you add to 3900, so what do you get? It should be 5050, so 1060 to 3990, 5050. Good job. If you have this in a way like this, then you finished your work correctly. Otherwise, please look at the code again, and you can find this code as you remember. Online. Now let's continue. So controlling loops with break and continue again. In a preceding program, you could see the that for each function we first validated the isPrime function properly determines the primeness of 1 through 7. So not only can you see that the sum of prime numbers and non-prime numbers, but you can also see the numbers in each set for further verification. So we expected 5050 and we got the result 5050. For a complete comparison of break, continue, return, and go to consider the following code outline. See here, and this outline, there is an inner for loop nested within an outer for loop. So inner, this one. Break will only go to the end of its immediate enclosing statement body. In this case, it goes to the end of the inner loop block. So here, only this here will be blocked or finished. In this case, it goes to the end of the inner loop block and executes statements in the outer loop block. Continue goes to the point immediately before the end of the enclosing statement body to repeat the loop iteration, and go to error immediately jumps to the error label at the end of the function body and handles the error condition before returning from the function. In the statement before the error label, there is a return 0 that returns from the function, thus preventing the execution of the error recovery statements. Now, understanding infinite loops. So far we have considered loops that have an actual end. In most cases, this is both intended and desirable. When loops never end, either unintentionally before we goofed up somewhere, or intentionally, they are called an infinite loop. There are a few special cases where an infinite loop is actually intentional. So here are the cases when the user interacts with the program until the user chooses to quit the program, and when there is input with no known end, as in networking where the data can come in at any time, and operating system event loop processing. This begins upon boot up and waits loops for events to happen until the system is shut down. When you start a program that accepts user input, keyboard strokes, mouse movements, and so on, it goes into an infinite loop to process each input. We would then need to use a break, go to, or return statement in the statement body of our infinite loop to end it. We don't get into this part because that is not intended in an introductory part of programming C language. Now, summary. We have encountered various repetitious looping techniques, from the ridiculous brute force iteration to the sublime various loop statements with break, continue, and go to, with functions, conditional expressions, and now as well looping statements. We conclude our journey through C flow of control statements. Nearly all of these concepts can be easily translated into other programming languages. In the bulk of the remainder of the book, so will broaden our understanding and ability to manipulate data well beyond the simple forms we have so far encountered. In the next chapter, we will move on and we will explore custom named values like enumerations. All right, so what we have done again, while statement, the for statement, the do while, then we talked about how they are interchangeable, and we used then the go to, and we used break and continue to control the loops as well. We talked about the situation where infinite loops are possible and could be useful, but we don't do them because we are not into that kind of situation right now. We continue now with chapter 8. So creating and using enumerations, that is our next topic. Thank you very much for your attention. Thank you that you have been here with me together. And now let's close it. Bye bye.